All right, here we go. So the first equation we have here is 16 to the 2x plus 3 equals 8 to the 4x minus 1. Our goal is to solve for x. And when you first see a problem you don't understand, a strategy, I'm not going to call it a bad strategy or a good strategy. A strategy is, hey, maybe I should just try some numbers. I should do some guess and check, right? Just plug it in there, see if it works. So I could say, like, what if x equals 1? Like, I don't know why I chose x equals 1. It just is a good number to try. If x equals 1 and I plug it in here, 2 times 1 plus 3 is 5. I get 16 to the 5th. And if I plug 1 in for this side, 4 times 1 is 4. 4 minus 1 is 3. I'd get 8 to the 3rd. So if I plug 1 in for x, I get this. Is this true? Is 16 to the 5th equal to 8 to the 3rd? Not even close, right? Bigger exponent, bigger base. There's no way those could be equal to each other. So x equals 1 didn't work. And then I could try like x equals 2 or x equals negative. I could try a bunch of numbers. But the problem is I don't know what numbers to choose from. When we were doing those polynomial examples earlier, we had that P over Q, the rational root theorem. I knew which ones to check. It could take me a long time to check, so I'd rather not go down that road. I'd rather have an actual strategy. If these two bases are the same, then I think I can make this thing work. So my first strategy here is, can you make it so that 16 and 8 have the same base? When you first added fractions, remember how you get a common denominator, right? So in these exponents, can you get a common base? Can you rewrite 16 and can you rewrite 8 so they have the same base? All right, what would that base be? 2. 16 is 2 to the 4th, and 8 is 2 to the 3rd, right? So I can write them both like this, and then I'll put the 2x plus 3 up here, and the 4x minus 1 up there. And this didn't write very well. I'll try it again. 2x plus 3 didn't look much better. And notice I put the whole 2 to the 4th inside of the parentheses here because this is the 16. What do you do with the 4 and the 2x plus 3 then? Do you know? You saw some of these on that graded worksheet that you had. If you had, let's say, x squared to the 5th, what would you do with the 2 and the 5? Multiply them, because this means x squared times x squared times x squared times x squared. And then you say, okay, if you're multiplying this, you'd add, you get x to the 10th. 2 times 5 is 10. You would multiply. So this is going to be 2 to the 8x plus 12 equals 2 to the 12x minus 3. And here's the good news of what we've accomplished so far. Initially, the 16 and 8 had different bases, but because we can change these bases, now they both have a 2 there. And since it's 2 to the this equals 2 to the that, don't those two exponents just have to be equal to each other? Like, that's the only way the left side could possibly be equal to the right side. 8x plus 12 must be equal to 12x minus 3. They have to be equal. So set them equal to each other. All right, so now, instead of having an exponential problem where we had those different bases, it's just turned into this linear problem. Can you solve that equation? A couple steps of algebra: add, subtract, multiply, divide, get the x by itself, solve for x. I got x equals 15 over 4. And I'll tell you, there's no way, like as I was starting this problem off with guess and check, there's no way I would have guessed 15 over 4 as a possibility. So having a method is actually going to be very helpful for this. So strategy number 1, get them into the same base. Get the 16 and 8 down to a base of 2, because then we can actually set the exponents equal to each other. So there's strategy 1. Strategy 2. This problem looks different. We need a new strategy. The first one was in exponential form. This one is in log form. ln of x minus ln of 4 equals 1. Turn to your friends, say hello, and then I want you to see what would you do to this equation to simplify it down right away. Do you have some ideas for this one? Go. Okay, let's see. These good news. These both have the same base that's positive, but we're subtracting them. And if you subtract the logs and you condense them into one log, what do you do with what's inside of those? Divide them. So step one, condense. Here is the condensing of that. ln of x over 4 is equal to 1. When you subtract the logs, you divide what's on the inside. But, and we're going to see this theme show up quite a bit, but now we're stuck. And when these problems are stuck, you convert. It's like right now we are stuck in this log form. We have to convert it into the other form, the exponential form. So as I look at this, it says ln, which is really meaning like log base e, right? I'm going to give you a quick 15 seconds again. Converting this one into exponential form, what would it look like? Go. Steph, why don't you move one to the left? You'll be with Delia, and then they can have their group of 3 there. Move one seat to the left, and you'll be with Delia. Okay, time's up. So log form to exponential form. It's going to look something kind of like this. It's going to be the base down here, e, to the first is equal to what was on the inside, that's x over 4. So it was in this form, which looks dead right now. Converting it, all of a sudden, oh, x is almost all by itself. One more thing algebraically then, how about multiply both sides by 4? And we get x equals 4 times e to the first, which is just e. So x equals 4e. For some of these problems, I'll have you get out your calculator and get a decimal, and we'll go back and check. But in this one, x equals 4e. Let's just leave it like this. Here is a nice exact answer. So strategy 1, get the common base of 2. We got the common base. They both went down to a base of 2. Number 2, we condensed these logs into 1, and then we converted to the other form. Okay, here's problem number 3. What I'm going to tell you about number 3 is do the basic algebra stuff first. The goal is eventually to get to x, but can you do some of the steps, add, subtract, multiply, divide, do some of those steps to simplify it at least a little bit? So let me give you just, again, a little bit of time here. Can you simplify this a little bit before we get to the more complicated, like exponential logarithm part of this? See what you can do. All right, step 1. How many of you added 2 right away? So plus 2 makes this 10. How many of you then got rid of this 2/5? You could divide by 2/5, but that's kind of hard to understand. Instead, you could say, I'm going to multiply by its reciprocal. Multiply both sides by 5 over 2. That gives us e to the 2x plus 1, which looks better than the original, is equal to 50 over 2, which is 25. So this blue looks better than the original black. It's not out of the woods yet, but it looks a heck of a lot better than the original. But once again, we're stuck. Just like this one where we were stuck in the log form, so we converted it into exponential. We're going to take this one, which is stuck in exponential, and convert it into log form. So it's going to be log base e because it's the base of the exponent also. What's another way to write log base e? ln. So it's the ln of 25 is equal to 2x plus 1. From blue to red, all we did is we converted, we changed forms, and now with the goal of solving for x, this red one gives me some hope. It was kind of dead in the water right there. There's nothing more to do with this equation except to convert to the other form, and now we're almost there. So from here, there's really only 2 more steps to do, and this is like more of a basic algebra at this point. What would you do to both sides next? Check the 1. So ln of 25 minus 1 is equal to 2x. One more step, what would you do to both sides? Divide by 2. So x equals the ln of 25 minus 1. I could say divided by 2. I could say times 1/2. I could distribute that to both of them. I could divide both of those different terms by 2. There's a lot of ways I could treat that are all equally valid and equally good. It's just a matter of preference. I'm going to leave it like this. Again, I could do more to simplify this thing down if I really wanted to, but I think this is good enough. I'm not worried about a decimal in this one either, so just leave it there. Evan.
No.
So were you thinking like call this ln of 5?
No, I was going to ask why can't you keep the other problem in ln and just subtract the 1?
So from red to green?
No, for the other problem.
This one?
Number 2, yeah.
So what was the question?
Oh, never mind. I see. Nothing. I was going to see if you kept it in ln for the other one, where it's like ln whatever minus a number. I was going to ask, why can't you just do it for that? So it's ln x over 4 minus 1. But then I realized.
Got it. Okay.
Wasn't really using the brain right there.
That's all right. All right, number 4. Number 4 looks like this. And quite frankly, it looks a lot like the previous one, but it's even a little bit better in that I don't have to add anything right away or subtract. I don't have to multiply or divide right away. Here's the starting point. And I hate to say it's good news, but I'm going to say it's good news in that it's stuck. It's stuck right now in this form. And when you get to these problems and you feel stuck, what are you going to do? Convert. It's an exponential convert. Convert to log form. So this is going to be log of what base? 3. Log base 3 of 2,000 equals 4x. Good. And just this simple conversion almost already has x all by itself. Now ask yourself, what do I need to do to get x all by itself? Wouldn't you need to divide by 4? Good. Divide both sides by 4. So x equals log base 3 of 2,000 divided by 4. And there's more ways than one I can write this. I could say 1/4 times all that. That would be totally fine. Here's the first time, though, where I want you to go and use your calculator. So if you don't have your calculator out yet, go ahead and get that calculator out. Know how to use the change of base formula. I would probably do alpha y equals choose the n over d for numerator over denominator. Put this in your numerator, divided by 4. And I'm going to have you round to 3 decimal places. I used to have people always round to 2 decimal places, but once I started teaching the AP calculus, they're always rounding to 3. So I think just as a habit and preparation for some of you who might be taking that class next year, round to 3 decimal places. So log base 3 of 2,000 divided by 4. And again, I want you to round to 3 decimal places. So when you put this in the calculator, was it 1 point something, 1 point?
1.7296.
7296. So it's the nearest 3 decimal places. That'd be 30. We call this 0 a significant digit. We're showing how precise that we've rounded it. So we think x is about this or exactly that. And this is the first time that I'm also going to have you check. Here's the original problem up here in pink. I want you to try plugging the 1.730 in for x. So 3 to the 3 with the little caret, 3 to the 4 times 1.730, then hit equals.
Yep.
No, we rounded, right? So was your answer close?
Yeah.
Like as close as we'd expect it to, maybe? So that's a way we can check these solutions. Like, was it like a little over 2,000 or a little under 2,000, Bradley? One of the, a little over. And if we'd been more precise with our answer, put more decimal places, the accuracy of plugging it back in would have worked out a little better for us. But again, 3 decimal places is what we're really looking for here. All right, number 5. Number 5, I'm going to pause again for a second, take a slow walk around the room. You can ask me a question if you like. And I want you to see what you can do with number 5, either on your own or with the friend who's sitting next to you. I know some of you have new people that you're partnered up with, but be bold, say hello. Tap them on the shoulder if you need to, if you're stuck or you want to help them out. But we'll be back in about 30 seconds to start going over this. See what you can do in the meanwhile.
No.
Will you do that one first?
It's true. That means most like x plus 2 is the x plus 2. Instead, we're trying to like dig in and get to x. Can you move the 1/3 to the other side?
Yeah.
So you don't have to worry about a cube root. I would much rather not work with a cube root.
Oh.
Thank you.
I edited this 40
You get like 15,000.
So similar, you know, like times in my music, like this up here, like here 2 times in by 5 2, just times it by 5.
But eventually you're going to run rid of 2 also. Wow. Okay, here we go. Number 5. The goal is to get to x. And I'm looking on the left-hand side, trying to dig in and get to that x. I see this 1/3 on the outside. It's 1/3 times all this stuff. How can we get rid of this 1/3 on the left? Times it by 3 over 1 by 3. So times 3 times 3. That gives us log base 5 of x plus 2 equals 6. This red already looks better. It's true, this 1/3 could become an exponent for the x plus 2, which means it's x plus 2 cube rooted. But by moving it to the other side, I don't have to worry about these cube roots. Here's where it's stuck. Here's where it's stuck. So we convert. It's going to be 5 to the 6th equals the x plus 2. So it's log of x plus 2. So it's x plus 2 already inside of there. We don't have to multiply them. They're already under one single log. Oh boy, 5 to the 6. 5 times 5 times 5, 6 total times. Big number, 15,625. Equals x plus 2. Oh, look at this. So close to having x by itself. Yes, it's a huge number, but one more step. Do what to both sides? Subtract 2. So x equals 15,623. So similar strategy that we've used before. Try to take care of the simple algebra stuff on the outside. Add, subtract, multiply, divide. So, and then eventually deal with the log when you have to. And a lot of times the biggest move we're going to make is to convert from one form to the other. All right, here's number 6. Again, let me give you a chance to see what you can do with this one. Think about what we've done before. We have 2 log-based 3s that are added together. What does it mean you're going to do with these things? When you're stuck, then try to convert. See what you can do.
Should distribute that 3x.
No, I think that's right.
But when you convert to exponential form, what is that going to be? Before, how many is 15,000 from here to 15,000 5 to the 6. Okay, from this, yeah. How do we get 5 to the 6? How's it going?
I thought I had the right idea, but now I do not.
You're close. It's just this 3 that's off right now. So in the last one, when we got this 15,000, like the 5 to the 6, which became the 15,000 number, how do we get that 5 to the 6? Because that's what you wanted. That's what's off.
No, I just got turned.
I don't know where
Oh, okay.
Okay, we all good with this first step? The log base 3s are added together, so we multiply what's on the inside to condense down to 1. Then we're stuck. And we're going to go to the other form. Into exponential form, what is the base in exponential form? 3. It's this 3. To the what power? To this power equals what's on the inside, the 3x squared minus 24x. So converting from log to exponential is going to look like this. It's 3 to the third. I saw a few of you who had 3 there instead of 3 to the third. So 3 to the third is 27. We're going to then subtract 27 from both sides. You might be saying, oh my gosh, that's horrible. I don't want to factor this when there's a number in front of the x squared. I saw some of you who are here and were really thinking about that one. My thought is, it's an equation. And in an equation, whatever I do to one side, I do to the other. What I would like to do to all of these terms on the left and the right is simplify them. Simplify by dividing by 3, which gives us still 0, which is very important. But it equals x squared minus 8x minus 9. And this green equation looks a heck of a lot friendlier than the previous one. Because that, I can factor. What multiplies to negative 9 and adds to negative 8? There is a pair, right? What are those numbers? There they are. So then x equals 9 and negative 1 once we have it factored. Thoughts on the answers? Do they both work? Up to this point, they have always worked. However, Alyssa, what do you think? Probably should check them in this case because we haven't got 2 answers before. If you checked x equals 9, it's log base 3 of 27 plus log base 3 of 1. That stuff is all good. But when you plug in negative 1, here's the issue. It'd be log base 3 of negative 3. Can you take the log of a negative? No. So you didn't do anything wrong through this whole problem. It's just that that was what's called an extraneous solution. Like it's extraneous is a combination of extra and erroneous. It's an extraneous, like it's wrong. Like it just doesn't work. So x equals 9 is the one and only solution. Even though we got this one, we have to check it. X is only equal to 9. X is 9.
And if you get only one answer, can you assume that that is the real answer?
So question, if you only get one answer, can you assume? I wouldn't do that. Hint, hint, wink, wink. Number 7. Number 7, I've given you a lot of hard problems so far. This number 7 looks a heck of a lot simpler, doesn't it? Like right at the very beginning, it's log base 10 of this equals log base 10 of that. They have log same base 10. If they both have the log same base, shouldn't the insides be equal to each other? Specifically, shouldn't 4 minus 3x be equal to 2x minus 6? Right? Those insides have to be equal to each other. Oh, I thought you were telling me something on my nose. So set them equal to each other. Now start solving for x. Add 6 to both sides. Add 3x to both sides. Divide both sides by 5. I get x equals 2. And I'm feeling great because I solved this one really quickly. Awkward silence. Go back and check it. Do we have an issue with this one? When you plug 2 in for x, what does this orange expression turn into? Log of -2. Can you take the log of a negative? No. And it doesn't matter that when I plug it into this one, I also get -2 over here. Does the log of -2 equal the log of -2? Actually, no, because neither one of them exists. Like, I don't care that these things look like exactly the same as each other. This actually, to the question asked just a moment ago, even with one solution, I would go back and check because in this case, we have no solution. It's impossible for this one to work. So the next question would be like, well, when do I need to check then? We weren't checking the first ones. We are checking these. Well, for the test or quiz, and I have the time, I'm probably always going to check, but I'm definitely going to check anytime I'm taking something out of log form and going into exponential form. I want to make sure that when I get a value for x, what's inside of the log doesn't become negative. And that's what the issue was in these last two problems. All right, to number 8. To get this one started, are you going to add or subtract anything right away? No, we're going to multiply or divide right away. Not exactly. Are we going to convert to the other form right away? No, because there's 2 logs on the left. So step 1 in this one, condense. ln of this plus ln of that. What do you do with what's inside of the ln's? What do you do with those? Multiply them. So it's ln of x squared minus 4x is equal to 2. So there's a good first step. Instead of 2 separate logs on the left, we have just 1 log on the left. However, at this point, it's stuck, isn't it? There's nothing more to do, so that obviously means we need to convert. And I'm trying to be very dramatic about that. Like, just think of that like being like sometimes like the ultimate savior in these problems. I'm stuck, convert. You can convert when you only have 1 log equals 1 number, or when you have something in exponential form with nothing else added or subtracted. And so we are stuck in this log form, convert into exponential. What is the base in this log? E. So it's e to the second equals what's on the inside, this x squared minus 4x. From blue to red, there's our conversion. We converted it into exponential form. It's a quadratic, so I'm going to get equal to 0. It looks like this. Oh boy. I scroll up earlier. Okay, we could factor this. We did a nice job of factoring this problem. How the heck are we going to factor this? The answer is we're not. It's not factorable. However, it is a quadratic, so it means we still can solve it. We can solve it using the quadratic formula. Ready? X equals negative b plus or minus square root of b squared minus 4ac all over 2a. So algebra 1, quadratic formula here comes back again. Negative b plus or minus square root of b squared minus 4ac all over 2a. And a is 1, so just 2. There's our answer, but this is not in an acceptable form yet. We need to simplify this down a little bit. So x equals 4 plus or minus all over 2, but now the square root. 16. What do you get when you multiply all of this back stuff that I have highlighted in pink? What is negative 4 times 1 times negative e squared? 4e squared. And it's positive now, right? So plus 4e squared. And while this looks pretty good, it still isn't quite done. Let me put the hold on this problem at least momentarily and go through like a slightly simpler problem and then show you how it relates to this. If I said, what is the square root of 40 broken down? What perfect square goes into 40? Yeah, it's not a perfect square. Try again. 4. 4 times 10 is 40. And why is 4 a good one to choose? Because what is the square root of 4? 2. So it would be 2 square root of 10. So we broke this thing down so we could simplify it to this. Right? Why is that significant? Because we're going to do the same thing underneath this square root sign. So little bubble here. Let's take this 16 plus 4e squared and factor it. Just like we did, 40 was root 4 times root 10, right? Well, what goes into both of these terms on the inside? What goes into 16 and into 4e squared? Bigger than 2? 4? 4 goes into both of them. So we could say this is the square root of 4 times 4 plus e squared. I'm factoring a 4 out of both those. And why 4? Because 4 goes into both of them. But also 4 is a great number. It is a perfect square. And I could say like this is square root of 4, square root of 4 plus e squared. Do we know the square root of 4 plus e squared? No. Do we know the square root of 4? Should. 2. So this whole thing becomes 2 square root of 4 plus e squared. Heavy in the algebra here. So x equals 4 plus or minus 2 square root of 4 plus e squared all over 2. There's an answer, but what goes into the denominator? This term of the numerator and this term of the numerator. What goes into all of those? 2. So that is why for our final simplified answer, we're going to divide them all by 2. And when we divide the denominator by 2, it's 1, it's gone. So we just get this rather unpleasant looking number. It is an exact answer. I'm not going to have you go to the calculator and figure out the 2 answers. There's a decent chance that I believe they are both going to work for this one. No, let's go ahead and do check that. On your calculator, do 2 plus the square root of 4 minus e squared. What does that come out to? Can you find that? So 5.3 something. Is 5.3 going to work when you plug them back in? I would say so because you're taking the logs of positive. Then do 2 minus the square root of 4 plus e squared. 2 minus that square root. Is that negative something? We having an issue with that one? Because when you plug that in for this part, you're going to take the log of a negative. That can't work. So the only answer then is going to be 2 plus the square root of 4 plus e squared. So we got rid of this minus sign down here because when we did the 2 minus that, it gave us negative. Negative didn't work when we plugged it back in. So this would be the one and only answer. Yeah, it's a great question. So the question was, is it possible that a negative number would ever work? So let's say we have the log of 4 minus x is equal to 7, something like this. Could you plug in like a -2 right here and like get a value? Could you plug in like a -10? Could you plug in even 0? There's a lot of numbers you could plug in. What could you not plug in for x to take the log of this? Like +5? Like if x was equal to 5 and you plug it in 4 minus 5 is -1, I can't take the log of -1. So in this case, a big positive number wouldn't actually work. So it depends on what's inside of here when you plug it back in. Sometimes negative is going to work. A lot of times the positive is, but sometimes the negative is going to be the one that works, not the positive. Good question. Okay. We've gone through 8 problems. I want you to look back at those 8 problems. Let me give you 30 seconds, and then I'm going to take any questions you have on any of those ones that you want to like just get clarification on. So look through those previous 8. So do we have any clarification questions? Anything we're not sure about? If not, we're going to skip number 9 for right now. We'll come back to that one tomorrow because number 9 is a very heavy problem. And in the roughly 7 minutes we have left in class, I know we're not going to finish number 9. But we can do number 10. So let's skip number 9, go down to number 10. The goal is to solve this one for x. So the goal is to solve this one for x. And this is what it looks like. Does this form look familiar to anything we've done before? Does it have like a sim kind of feel to it as anything you've seen before? It kind of looks like a quadratic, doesn't it? Like instead of this, what if it was x squared minus 3x minus 10 equals 0? Like it looks kind of like that, doesn't it? How would you factor this one that I just wrote? Minus 5 plus 2. It would factor like this, right? Okay, so keeping that in mind, how do you think you're going to factor that green one? And I'll tell you, it will actually factor. How do you think that green one's actually going to factor? Close. Very close. Negative 5 times 2 is negative 10. Great, we needed that. But what's e times e? E squared. What do we want it to be? E squared x, e to the 2x, right? So what exponents would you put up there? What if it was this? What's e to the x times e to the x? E to the 2x, which is what we want, right? And when you multiply these insides, there's negative 5 e to the x. Multiply the outside, there's positive 2 e to the x. Combine those, there's our negative 3 e to the x. So by recognizing this is just like the quadratics and kind of factoring it what it was just along that form, I have the same idea. Instead of x, it's e to the x. So here it is factored. Not solved, though. If I go back to the one that makes a lot more sense to us, if I was going to finish solving this one, I would set this part equal to 0 and then solve it. I would set this part equal to 0 and then solve it. So over here, it's the same thing. We're going to set e to the x minus 5 equals 0. So e to the x equals 5. So we set it equal to 0. E to the x equals 5. It's stuck. We've had plenty of these today where we're stuck. So what do you do with this? Convert. So it would be log base e of 5 is equal to x. Great. There's a solution. And because of the time left in class, I'm not going to have you plug it in. I'll just tell you ln of 5 works. And then for the other one, we'd say e to the x plus 2 equals 0. Subtract 2 from both sides. And then look at this equation we have. Do you see an issue with that? Can you take e to a power and end up negative? No, and if I tried it, I'd be saying ln of negative 2 equals x. Big red flag here. I can never take the natural log of something negative. So ln of 5 equals x is the one and only solution.